Let's start with the reaction. 2N2O5 becomes 4NO2 plus O2. Okay. Now, let me just put in carbon tetrachloride. So this happens in carbon tetrachloride solution. And I'm actually going to, you know what, let me actually write the equation again up here. 2N2O5 goes to 4NO2 plus O2 in CCl4. Okay, so now we have some time measurements and we have some concentration measurements. N2O5. Okay, so 0, 200, 400, 600, 800, 1000, 1200, 1400. We have 1.00, 0.88, 0.78, 0.69, 0.61, not 71, 0.61, 0.54, 0.48, 0.43. Okay, so we have this set of data that we collected. At different time increments, we measured the concentration of the N2O5, and sure enough, it's, you know, it is decreasing. So now, when we graph this, I'll just do the graph right here. You're going to end up with something like, if this is 1, start off with 1. Let's go ahead and put 0.2 down here. And let's put 400, 800, 1200, 1600. So it's going to look something like this. This data just plotted on a graph. Okay? 400, 800, 1200, 1600. Nice and simple, nothing particularly complicated. This is time. This is concentration of the species. Okay, so now what we want to do is we end up actually, okay, so now I'm going to leave this here and I'm going to move to the next page. When I take that graph and I pick a couple of points, I can actually measure the concentration of N2O5 at particular points. So when I do that, I have the following, and I can actually measure the rate, the instantaneous rate. Remember, you draw tangent lines at a given point, you measure the rate at that, you measure the rate someplace else. Okay, so at a concentration of 0.90 moles per liter, the rate ends up being 5.4 times 10 to the negative 4. 0.45, 2.7 times 10 to the negative 4. Now, notice what's happened here. At a certain concentration, I measured the rate of the reaction with a tangent line. At another concentration, I measured the rate, but notice the relationship between these two. I did this specifically. This is half of that. Well, this is half of that. What happens here? The correlation, this also happens to be half of that. So when you have something like that, where, so when the concentration is halved, the rate is also halved. It won't always happen like this, just as happens to be this particular data that we did. We arranged it so we can check the rate at concentration that is easily comparable. So 0.9, 0.45, this is twice that, this is half of that. So as it turns out, when I have the concentration, the reaction rate is also cut in half. That's a linear relationship. That's the whole idea of it. If you double something and the thing that you're measuring also doubles, that's a linear relationship. If you double something and the thing that you're measuring goes up by a factor of 4, that means it's a quadratic relationship. 2, 4, 3, 9. Here you've halved it or doubled it, depending on which direction how you want to look at it. Here you've doubled something. The difference is double. So it's a one-to-one relationship. That means it's a linear relationship. Linear means an exponent of 1. So our rate law is this is the symbol. Let me write the rate. In fact, oftentimes you don't really need the symbol. I know that this symbol actually confuses a lot of students. It does me too. I don't particularly care for it very much. It's just a symbol. It means rate. For all practical purposes, you can actually leave this off and just write rate equals. And we said that the rate equals some constant K times the concentration of the reactant, N2O5, raised to some power N. Well, here, because the relationship is linear, and I read it straight off, when a concentration is halved, the rate is halved, or when a concentration is doubled, the rate is doubled. That is a linear relationship. That means N equals 1. So I don't need this. So this is the rate equals some constant K times N2O5. That means the rate of this reaction, based on the data, is actually some constant K raised to the concentration of the dinitrogen pentoxide raised to the first power. This is the differential rate law. This is the differential rate law for this particular reaction. So the most important thing to take away from this, the most important thing to take away from this is that under conditions where we actually measure rates near points where the reaction is just starting, where we have a concentration and then another concentration, we have the rate at one concentration and the rate of the other concentration. When we see how the concentration changes and then we compare it to how the actual rate changes, that gives us the exponent of the particular concentration term of the reactant. That N is called the order of the reaction. This is a first order reaction. So the decomposition of dinitrogen pentoxide is a first order reaction. Now, I'm going to go ahead and stop this lesson here. I just wanted to give you sort of a brief rundown about how this works. Next lesson, we're actually going to get deeper into this, and we're going to calculate differential rate laws, we're going to calculate the exponents, and we're going to calculate the rate constants more systematically. But I just wanted you to see and get a sense of what this looks like and how things operate. So thank you for joining us at Educator.com. We'll see you next time for a greater discussion of kinetics. Bye.